Greetings everyone, today we're going to explore graphing quadratics using Vertex form. You're going to need a ready utensil and the two example handouts that I provided to you to take notes on. Let's recall our absolute value shifts. When we talked about did it shift left or right, did it have a vertical shift up or down, did it reflect in the x-axis, and did it have a vertical stretch or compression? If we think back, let's relate how absolute value compares to quadratics. When we had a number on the outside of the absolute value, that was our vertical shift. So our vertical shift in this case meant up 2, and our vertical shift here meant down 4. Now with quadratics, it means the same thing. If it's on the outside, this would mean up 2. On the outside, this would mean down 2. If we take a look at the number inside the absolute value, that was our horizontal shift. Horizontally, remember, we had the opposite sign. So a -5 actually meant right 5, and a +5 actually meant left 5. We had to be very careful with those signs. The same idea applies when we have quadratics. If it's on the inside of what's being squared, the signs are still the opposite, so this would be right 5, and this one will be left 5. When we have a negative on the outside, that means it was a reflection in the x-axis, which meant it was a v that went down instead. Well, same thing, if I have a negative on the outside of my x squared, that still means it's reflected in the x-axis, which means it's going downwards. So when we talk about open, that means down, and we've already dealt with that a few times. We also, of course, had our numbers out front of our absolute value, so a 1/2, and then we had a 2. Remember the 1/2, if it was less than 1, what word it means less or means smaller, compression or stretch? In this case, compression. And if it was larger than 1, that's when it was a stretch. Same thing applies if I have a value outside of my x squared, or if I have a value outside of my x squared. So the rules of absolute value shifts apply the same way for absolute values as they do for parabolas. Jot this down somewhere around your notes sheet. We want to take a note of our vertex form. Notice it looks the same. Imagine that these were absolute value signs instead of parentheses. It looks the same as our previous notes then. So let's read left to right. Vertical stretch or compression is going to be your value on the outside. Remember, stretch is when your a value is greater than 1. Compression is when your a value is between 0 and 1. Typically fraction, right? Your horizontal shift. Remember, notice the subtraction sign is part of the formula. So that's why it always looks like the opposite. So if I have an x minus 2, that means to the right. If I have an x plus 2, that means it's to the left. And then we have our k value, which represents our vertical shift. So if I add on a 3, that means it's up. And if I subtract a 3, that means it's down 3. Take a moment if you need to pause this video to take the notes. Let's take a look at our first example to go on your first sheet that I handed out. Take a look how different that vertex form looks compared to your standard form notes we took. We're going to look at 3 forms, so this is our second one. Our approach here is going to be different than our standard form. We're going to start off by creating a parent table. Now we did table work when we had absolute values, but we didn't do it very often. And so we're really going to stick to it for our vertex form. So parent table, we create it using the parent function. Parent function is what this is. It's a quadratic. So a quadratic is just y equals x squared, meaning there's no moves or changes to it. What's the parent function? Where did it come from? So to create the parent function, we actually start off with those standard values that we always use. And we plug in those x values in for x up here. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. This parent table will be the same for every quadratic. So if you filled it out once, then you filled it out every time. Now what we're going to do is we're going to apply our transformations. So to do that, we got to look over at our equation, our function, and we want to see how many moves we have. Well, I have this 1/2, I have this -3, and I have this -5. So I have 3 moves I'm going to take care of. The first move says 1/2, and it's being multiplied. So I want to multiply by 1/2. This case, it's a vertical compression. Vertical means I'm going to multiply the y values. Your compression or stretch always applies to your y values. Next to every y value, I'm going to multiply by 1/2. Take a look at the next move. The next move is -3. That -3 is inside parentheses, so that is our horizontal shift. Now this horizontal shift, even though it says -3, that means to the right 3. Horizontal means your x values. So on every x value, I'm going to add 3. So we're just applying each transformation. The -5, that's my vertical shift, which means it's my y values, and they are as is. This means down 5. So I'm going to subtract 5 from each y value. Now you want to go in order. Order of operations matters here. Now for the transformations, we're just going to do the math. We're going to take care of what we said in the parent table. So -2 plus 3 is 1. -1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. Left side's done. Let's take a look at the y values, your right side. 4 times 1/2 is 2. 2 minus 5 is -3. 1 times 1/2 is 1/2. 1/2 minus 5 is -4.5, or -4.5. 0 times 1/2 is 0. 0 minus 5, -5. 1 times 1/2 is 1/2. 1/2 minus 5 is -4.5. 4 times 1/2 is 2. 2 minus 5 gets me to -3. So here I can see my symmetry, and I'm going to graph this function. So I'm at 1, -3. I'm at 2, -4.5, and that's okay. -3, -5. -4, -4.5. -5, -3. This is a parabola, so make sure it's got that curve to it. Now make note that this is pretty wide. This is a wider U. Why? Because we had a compression. Remember, as you compress the U, it squishes it, it spreads it out. Let's start answering some of our questions. I know because the function is positive that it always opens up, and I can tell by my graph. Here's that same graph that I've carried over. Our vertex, we can tell from our table. If you look at your table, your vertex was at 3, -5. Your axis of symmetry then also occurs at 3, and it's going to be x equals 3. Maximum and minimum. Well, my maximum or minimum is my vertex, but in this case it's a minimum. Our y-intercept. I don't know what my y-intercept is. Now look at your graph. Your graph we didn't extend, so we're not sure. So here, add this reminder. Y-intercept means 0 for x, and you'll get a number for y. X-intercept means a 0 for the y value to find your x values. let's start with y-intercept. It's always the easier option. So in this case, I'm going to take my equation, and wherever there is an x, I'm going to put a 0. So this is the same as standard form, you guys. We're just plugging in for 0 for x and seeing what we end up with. I need to see work here. If you do not show work, I can't give you credit or a check mark for your notes. -3 squared is 9. Half of 9, I could leave that as 9 halves, or I could say 4.5. 4.5 minus 5, we end up at -1/2. Now we know we have to write that as a point. Intercepts are always points. And if I was to extend my graph that I originally created, that makes sense. Now we want to take and we want to put 0 in for y and solve for our x values. In standard form, when we did that, we had to either possibly factor, use quadratic formula, or completing the square. But here, we're going to solve by square roots. So this is another good review of last unit. That's why we needed last unit, so we could use it to figure out our actual graphs. So I need to isolate the x value, which means I'm going to move the 5 over first. I'm going to divide by a half next. 5 divided by a half, you guys, I'm not dividing by 2, I'm dividing by a half. There's a lot of errors on the last assessment. That is 10. 10 halves go into 5. I'm still trying to isolate the x. Now I can square root because everything's being squared. I have plus or minus radical 10. Don't forget your plus or minus. I'm still trying to isolate the x. I'm going to add 3 to the other side. When I add 3, I cannot combine because they are not like terms. So I'm going to put the 3 out front so that it's in that sort of standard form. Now it's an intercept. You're supposed to write intercepts as points. So that means I have 2 intercepts, 2 x-intercepts. I have 3 plus radical 10, and I have 3 minus radical 10. Now in this case, if you want to check your work, plug that into your calculator, see what the decimal value is approximately. If I take a look, 3 plus radical 10 gives me about, and you don't have to write this down, but it's about 6.16. If I do 3 minus radical 10, I end up at about a -0.16. If I take a look, that makes sense. If I was to extend my graph, if I was to check it on Desmos, yeah, it's about at those points. So I feel good and confident in my answer. Domain and range, remember, domain's your freebie. Parabolas are always -infinity to infinity. My range, the lowest it goes is -5, the highest it goes is infinity. We include -5. Increasing, decreasing. Remember how we approached this with standard form, the examples we did in class. We know we're going to have 2 intervals. I know I'm going to go -infinity to infinity. And I know my vertex point of 3 is where I change direction. Start there, then label if it's increasing or decreasing. From -infinity to 3, I'm going down. Therefore, I'm decreasing. From 3 to positive infinity on the x-axis, I'm increasing. So again, remember on this one that you're always going to have 2 intervals. You're always going to use that axis of symmetry. You're always going to have -infinity to infinity. Approach it that way as a way to remember. Let's take a look at our second example. We want to start off with our parent table. These are still parabolas or quadratic functions. So your parent table is still going to be the same as it was before. We're going to start off with these standard x values. Oops, let's fix that. If I plug it into my parent function, I'm still going to end up with 4, 1, 0, 1, and 4. That'll be true for every parabola. Let's take a look at our moves. I have a reflection in the x-axis, and I have a vertical. In this case, it's greater than 1, so that's called a stretch. What's nice is we're going to combine this into one move. It's vertical, so it applies to the y's. We're going to multiply every y value by -2. So the reflection and the stretch or compression are one calculation. We then have a -3 horizontal shift, so that means I'm going to the right 3. So I'm going to add 3 to every x value because it's horizontal shifts. And then for my -4, that's my vertical shift, which means down 4. So I'm going to subtract 4 from every y value. If I apply these calculations, I'm going to have my new table. -2 plus 3, -1 plus 3, 0 plus 3, 1 plus 3, 2 plus 3. This happens to be the same as the last example. That won't always happen, of course. My y values. 4 times -2 is -8. -8 minus 4, -12. 1 times -2 is -2, minus 4, -6. 0 times -2 is 0, 0 minus 4, -4. 1 times -2, -2, -2 minus 4, -6. 4 times -2 is -8, -8 minus 4, -12. So I can see that symmetry here. I'm going to graph these points. You'll notice 12 is off of our scale, so I'm not going to worry too much about it. But let's graph 2, -6, 3, -4, and 4, -6. So you'll notice this ends up being a pretty steep or narrow parabola. Well, that makes sense. It's a stretch. We're stretching out the u. I can then go through and answer some more questions. It opens down because the leading coefficient or the leading value is negative because it's reflected in the x-axis. It's down. Let's answer some of the other questions. My vertex was on my table, and that was at 3, -4. My axis of symmetry, therefore, is x equals 3. My max or min is my vertex, but in this case, it is a maximum. Okay, these questions should start going this quickly as you answer them. Our intercepts. This should be automatic. X-intercept means 0 in for y. Y-intercept means 0 in for x. If I plug in 0 in for x, find that calculation. Take your time with that mental math. -18 minus 4. So we end up at -22, but we write it as a point. Well, that makes sense. If we look at our graph is really steep. So in this case, that makes sense for where it is, but you have to do the work in order to tell me that y-intercept. Also note that I need to see these calculations, this work shown out in order to get your check mark. Now let's plug in 0 in for y. Remember, f of x is just function notation. We can replace it with a y, and that's where our 0 then goes. Because we're in vertex form, we're going to solve by square roots again. So I want to isolate this x, move everything away from the x. So I'm going to add 4 first. You'll notice that with vertex form, this becomes pretty scheduled in the sense of we do this, then we do this, then we do this every single time. Next, we divide by -2. Now I can isolate the x by square rooting both sides. Plus or minus. Then we can add the 3 over, and I'm going to put it out front. Now I need to reduce. I have a negative under the radical, a negative comes right out front and becomes an imaginary. 2 does not reduce any further. Radical 2 does not reduce any further. So in this case, remember we write these as points. We need to see 2 points. We have 3 plus I radical 2 and 3 minus I radical 2. Now I can't plug that in my calculator and it's imaginary. So if we think about it, yeah, this graph does not cross the y-axis, or excuse me, the x-axis anywhere. That's why they're imaginary. So we have an algebraic solution for the intercepts. Graphically, we don't see them because they're imaginary. Here's your freebie. Domain should be automatic. Range should be pretty quick, low to high, bracket, parenthesis. Increasing, decreasing. Remember, you'll always have 2 intervals. You'll always go negative infinity to infinity, and your axis of symmetry will always be the point. From negative infinity to 3, I am increasing. And from 3 to positive infinity, I'm decreasing. So we went over 2 examples. I'm going to check those in class for a check mark. Make sure that you keep up on a homework. And if you're working towards a reassessment, make sure you're taking care of that, getting that in, because next week is the end of the semester, so we're running out of time to get everything caught up. So make sure you take care of all that. If you have any questions, let me know, and we'll see you next time.